This section that we'll start with today will be, I put it in quotes, I call it planar elements. Not all of them necessarily act in a plane, but usually when we start to model them, we see them in a plane, and for most of these, the deformation is in the plane. So we'll specifically look at plane stress and plane strain, element types that you've probably heard about a lot, hopefully neglected a lot as well. Slight variation on the plane strain, they're called generalized plane strain. We'll talk about axisymmetry elements and some of the special variations of it as well. But then there's also additional special elements that we're not going to talk about. If you at any point want me to do that, we can add a session on that as well. So stuff like shear panels and cohesive zone elements and so on. Now, these in white is nearly useless. Okay, I say this for a very specific reason. I'll sometimes add something that sounds shocking at first. The key being nearly. These elements are not useless, but in most analysis types that we do today, none of these are applicable. There are very special cases. In those cases, the ability to model with this is actually really useful. So let's start with the plane stress element that is modeled. All of my definition here, when I talk about the X and Y plane, it's kind of like your screen. You're looking at it normal to the element. So there's no stress normal to this. So Z in all of my models will be in the thickness direction. So there's no stress in the Z direction, but there can be a strain due to Poisson effects. Okay, so I just in gray mark there, unless it's unloaded, then obviously the strain in the Z direction will be 0. Okay. To model this, the structure has to be thin, it has to be a planar structure, and it has to be loaded in the plane only. So that means either a tensile or a shear load in the plane only. I specifically exclude compression. Yes, we can model it, but you have to be careful because this element cannot move out of plane, so it cannot model buckling. The moment you have compressive load, you'll introduce buckling. Yes, when you apply a shear load, we can also get buckling, so that's also kind of a special case. So just be careful of this. So this is the classical example of when we'd want to use this. We've got a thin plate with a hole in it. I want to calculate the stress concentration for those. So I've got a structure and I apply some kind of an edge load to this, perfectly balanced. Yes, I want to mesh finer. This is just the visual representation. But by the way, we could just as well have used the shell element instead of a plane stress element because they're exactly the same, except the shell element allows bending. It allows movement out of the plane as well. So as long as if this is a shell element and I constrain either all of these nodes or just a couple in the Z direction, I'll get exactly the same answer. The shell element may run a little bit longer, and by running longer, we're talking fractions of a second. So again, it's not important. Okay, in terms of the real world, when do you use this element? So if I do a coupon test, let's say something similar to a thin plate that you want to do a necking test on, like this model here, stress concentrations. What we often see is in classroom test models. It's very easy and convenient to do an exercise on something like this. But again, in terms of real world, we seldom see this kind of a structure as the full model. Then the opposite of that element, the plane strain element, it looks the same. If you run it, you can apply the same loads. But the difference with this element is there's no strain in the thickness. In other words, the Z direction. There is a stress in that direction though. So the requirement for that first one says I'm clamping my structure between two infinitely rigid walls, and it's not allowed to either stretch or shrink. So if I go back to this model, if I extrude this in the thickness, and assuming it's rubber, and I glue it between two infinitely stiff stuff like rigid steel, and that'll be the kind of a model that I have here. So in this case, sorry, read out of plane. So it's structures that constrained out of the plane, but it's loaded in the plane only. Okay, so the only common, reasonably exact model would be something like the initial gravity dam design that we can do, something like this. So This is the rock below the dam, the downstream, upstream water levels. And in the thickness direction, this is constrained by the rock walls it's attached to. So in theory, it doesn't allow expansion in that direction. In practice, there will be a little bit, but hopefully small enough that we can neglect it. So there's an example of structure like that. Be aware that I specifically did not include the gravity arch types dam. So if there's an arch, you cannot use this. So in this case, we say the strain in that direction is 0, and we do a cutting plane somewhere over there. We already see a couple of interesting complications to the assumption. One of them, that angle is not quite vertical, so we already have some slightly strange strain in that direction due to that stiffness at that location. In addition, we've got these buttresses or stiffeners, depending on the industry you're in, that we cannot model with this because the assumption is it's one section and that section stays constant. Yes, we can neglect those, but for a first order answer, I can get a reasonable answer. There's actually an additional problem here that's not that clear on this image. Let's go to the next one. There you can see it a bit better. So we've got this really large structure there, but a smaller one on the inside. For this one, the assumption that these are infinitely stiff in this direction is actually pretty reasonable. So I can do the design for this, but not so much for this using plane strain. Okay. Now, one of the things that I see quite a lot, especially in university and so on classes, is that this element is being used to model thick structures. So just getting back to this image again, if this was a really thick structure, common way of modeling would be to say we do it with a plane strain element because there can be no strain in the z direction. No, that's not quite true. I'll show you now why. So this is that same model that I've got pretty thick, and I'm applying in this direction, exactly like that initial model, a load in this direction. I've modeled this one so that there's 0 stress concentration. It's a perfect tensile pressure applied to those and just enough constraints to get this model stable. So there's the results for a section that is an eighth of a section. So I've got a quarter over there and it stops at the halfway mark. So this bottom section over there is the halfway mark. And if you haven't done this before, at first glance, it seems like the stress should be constant through the thickness. I mean, it's a constant section through the thickness. I'm applying a constant pressure, but I get a varying load. If I look at the Z component of stress, at the top, you see there's very little in the Z direction, the Z being that length direction, so the thickness effectively. But as we go in, it stabilizes to a value where there is definitely a reasonably well-defined stress through that section. Okay, just the same model. I've just removed the edges so there's a bit more visible. If I look at just one slide back there, that first row of elements, and I plot the same result, but just for those. If I look at the scale, you can see it's a lot less than that. And for most of this, the stress range is very close to 0, while there on the outside, it's even less than the inside. So if I model this thinner, I get closer to a 0 stress, but it won't be perfectly 0. So this is effectively the same. That first layer that you see there has got the same behavior as a plane stress. If I look at the strain in the Z direction, and this is where things get ugly, the strain in the Z also stabilized, but in the bottom, there's now a constant strain. And the assumption usually says, well, 0 strain, but it's not 0. If I look at that scale there, that's somewhere around about 2. Just for clarity, that should have been E minus, which is the visual thing, to make the image a bit smaller and easier to see the scale. Okay, if I take that bottom row of elements and I plot the strain in Z, yes, it looks like there's a gradient, but over there you can see there's not really. It's just a very, very small change from there to there, but it's not 0. So if I compare this, the answer, if I go back to the stress state at the bottom, the stress at the top, the average stress will be better represented by the plane strain element, but it won't be correct. It'll just be more reasonable. Okay. And this is an exaggerated plot of the deformation in just the z direction. So that load is still applied, but it's just harder to see this radius once you do that. And there you can see the different locations that moves different amounts towards the inside. But this bottom section with a constant strain mean that section there is maybe stretched in that direction and it shrunk in this direction, but it stayed very close to flat. It doesn't have this kind of a deformed shape. So that's where the generalized plane strain element comes from. This element says there is a strain in the z direction, the thickness direction, but it's constant. In other words, every single element in the model is forced to have the same amount of strain. So if I rerun the same previous model with this, I'll get to the stress state that I'll see at the bottom there. But I won't have, or I'll have a constant strain in the z direction of that, what was it in this model, 0.0002. So 2e minus 4 strain in the z direction. Okay, so while that is not critically important, it does change your answer. So if you need to be really accurate, you have to model something like a generalized plane strain instead of a normal plane strain element. So when do you use this? If you have very thick structures, so like this model that I've got, but still loaded, and I now put it in quotes for in plane, it's kind of in the section. So if I look at this again, and I cut the section through that, that section stays more or less constant. Well, it stays perfectly constant in this model. So this is why, when and why we want to use this. Okay, then we get to another type of element, and I'll halfway switch forward and then just back again to complete the slide. So any kind of an axisymmetric structure, and if you don't know what it is, you'll see in a moment, but I assume most of you, all of you do. Any axisymmetric structure with an axisymmetry load, and there's a minor additional thing that says the results has to be axisymmetric as well. So I'll get to why I add that additional comment in a little bit. Okay, so if we look at the most basic axisymmetry element type, we only have a radial and an axial degree of freedom. So if I just switch to the image, so this is typically what the element would look like, but it represents that full section, and yes, it's completed. It's just so that you can see what it looks like on the inside. So that little face there effectively represents that whole section. So in this model, that'll be the radial direction, and this will be the axial direction. So it does not have the ability to move normal to the element itself. And I'm talking about the most basic axisymmetry element type. Okay, so every element type that you have is actually one order higher than what you'd expect. So if I look at that, that looks like a surface element, but it's actually a solid. If I had a curve and I revolve that, that's a surface. If I have a point, that's revolved into a beam element. But we're looking at it only in this plane. And the reason for that is, doesn't matter if I cut it there or there, any plane, if I look at the stresses normal to that, the displacements, I'll get exactly the same behavior. As long as the structure is axisymmetric, the loads are axisymmetric, and the results is axisymmetric. So why do I say the results has to be axisymmetric as well? There's two cases where I can get a structure that's symmetric or axisymmetric. And the loads are again correspondingly either symmetric or axisymmetric. The constraints are, but the results is not. And those will be for modal analysis and for buckling. If I look at the structure, if I want to load in this direction, I can model that kind of a buckling shape, but I can't model this thing buckling out of plane, because my assumption is if a node moves in that direction there, so it means that one moves up and this one moves down. I cannot get a bending effect using this kind of an element. Okay, so the kind of loads we can apply to this element is we can apply a radial load, in other words, internal, external pressure. It can be also due to a shaft that's spinning. We can even have contact between an inner and outer part. So again, I can have another axisymmetry body there making contact there, possibly with interference fit, and then as you spin it up at some point, you may find that those two separate. The other type of load that we can have is an axial load. So again, getting back to this image, I can apply a load in this direction, which means it's a pressure applied over the whole face. In terms of the rigid body motion of this structure as is there without any constraints only has one rigid body motion. That's movement along the axis. The reason for that is if that node moves up, the radius increases. If the radius increases, I've got an increase in stress because that circumference becomes larger. So there's a strain in that direction. So the minimum constraint that you need to apply for the model to run, I'm not talking about accuracy, just to be able to run would be a constraint in that direction. If I look at all the previous elements, the plane stress, plane strain, and generalized plane strain, I needed a constraint in the X, the Y, and some way to stop the rotation about the Z direction by constraining, argument's sake, two nodes with a moment arm in X or Y direction. Good. In terms of the results, the motion we see is in the plane only. So again, radial motion means the whole thing stretches. I can see stresses in any of the directions, X, Y, and Z. So in other words, axial stress, radial stress, and circumferential normal stresses. But in terms of shear stresses, I can only see the in-plane effect. So getting back to this, if that lifts up and this moves in, that angle change, that shear strain I can see. But for both other shear strains, this has to move normal to the plane. Otherwise, it's impossible to calculate the shear strain in that direction. Okay, so the real world use is pretty much anything that rotates. In some cases, we'll have a model that doesn't rotate, but it's still a symmetrical structure, a cylindrical axisymmetry structure. But in most cases, we're looking at stuff that's spinning. One example would be a flywheel, but lots of shafts for structures is pretty often modeled using this. Now, a comment that I just need to make, up to now, we only looked at the most basic axisymmetry element. So there are finite element software that allows a normal motion of those nodes. In other words, in those cases, you can also model a torque on the shaft. So while in theory that's not perfectly an axisymmetric load, if you just redefine axisymmetry, it's still a valid and a viable kind of a model. But then you have to change how you constrain the structure because you have to then constrain that normal motion of the structure as well. Okay, then a more complex topic is Fourier axisymmetry. In some cases, we have a structure that's axisymmetrical, but the load is not axisymmetrical. So I can have, if I just switch forward, it'll be easier to read the rest of this. If I have a shaft that looks like this, but I've got a load applied like that, but it's not all the way around. So that's not axisymmetry. I can model this using Fourier axisymmetry by applying that load there, but then specify that load as a function of the theta direction. So that being the theta, the circumference direction. So getting back to the previous slide, so the load can be a function of that circumferential position. But one of the issues that we now have is the results is therefore also a function of that circumferential position. So what this allows us is more complex loading on structure, something like a pulley on a shaft where the load is applied similar to this in one direction. If I've got a belt running along there, the load is in this direction, but not all the way around. And the other one is we can now do rotor dynamics on more complex structures than we can do with simple beam models. Okay, so that also allows movement out of the plane. In terms of how this is set up, we have to specify Fourier coefficients to specify that load as a function of the theta direction. For those of us that haven't used Fourier coefficients or Fourier methods in a while, it's simply this sum of a series of sine waves approach that defines the load. So I can specify, argument's sake, the pressure varies as sin of, and that's one revolution, plus sin of double that frequency along there. And by doing that, I can model a complex load distribution using this approximation. It's not going to be exact for this kind of a load where if those are all the same load and then zero afterwards, I'll have some kind of an approximation where the load may do something like this and then spike and then a little bit of variation and come down again. But we can do that really well, and the more Fourier coefficients we use, the closer we can get to the actual load that we wanted to model. Finding out what the Fourier coefficients are, if you manage, it's usually a bit of a pain, but most software, or at least some of them, allows you to specify the load as a function of angle, and you simply have to specify how many Fourier coefficients, and the software that will then calculate what those results are. The downside to this method is your result is now a function of, well, Fourier coefficients as well. So the result at this location will differ to that face, to that plane. All of those will be different. So now as part of the analysis, we also have to then say, I want the results at 0 angle, 10, 20, 30, 40, 50, whatever the case may be. We can specify which angles. And the software will then take those Fourier coefficients and the relevant angle and convert that back to results at that location. So I'll see all of them in the same location in space, but I'll see, let's say this as being 0 angle, then a 90-degree angle would be a separate result and may deform differently different stresses, but I'm looking at the results on that plane then. 180 it would be at the bottom, so that section, and so on. So in other words, it's a bit more painful to post-process this, but it's worthwhile in terms of runtime. It means I can, for this model, I can have a lot finer mesh there than I'd use for this one to have the same total number of elements, or I can use a lot less element for the same accuracy of answer. So it's a really convenient way to do things, but again, it's very limited in its applicability. Okay, so in summary, the planar elements that we looked at were the plane stress elements. So it's thin planar structures that's loaded in plane, membrane kind of structures that's in tension effectively, in other words. The plane strain elements for much thicker structures that's constrained on the size as well. For a first order answer structure, unless you have access to the generalized plane strain element. If you do not have access to a generalized plane strain element in your finite element code, it's actually really easy to do in any case. So you can model this using solid elements with a single layer. You constrain the bottom face vertically and the top face with an MPC equation. You force all of those nodes to have the same displacement in the Z direction, the thickness direction, in other words. So it's slightly more work, but you'll get a more accurate answer than you get trying to use plane strain element for thick structures. Okay, and then we have the axisymmetry elements, which is used for all kinds of spinning or shaft-like structures, except for shafts, usually there's bending, and the axisymmetry element, other than Fourier axisymmetry, cannot model it. So in short, all of these elements are seldom useful. It doesn't mean they're not useful, they're just seldom useful. You have to be careful of when and how you want to use them. Probably the most commonly used one, or the most applicable, will be axisymmetry, because there's lots of industries that actually use stuff that spin significantly, and the approximation is really good for what they're interested in. And then specifically in civil engineering, the plane strain for gravity dam design is also used a lot. All of the others tend to be for very special, very simple applications. Okay, so what we spoke about in this section was the planar kind of elements. We've already spoken about all of the others. Just a brief mention of an additional planar element is the shear panel. So a shear panel element, again, if I go back to these, it looks the same as, come on, this kind of image. It looks like a shell element. The shear panel element, though, can only transfer shear loads, although there's sometimes a way to add additional slight axial load transfer capability as well. So why does that element exist? The reason is if you have a very thin membrane and you apply any kind of either a bending load or an actual compressive load, that is going to buckle 100% guaranteed. But that doesn't mean that element cannot still transfer shear. If you look at the design of aircraft wing, for example, it usually has a very thin skin, especially the older, well, not necessarily older, but the thin metal skin ones, which means that they're guaranteed to buckle for certain types of loads. If you look at the pressure at the bottom of the wing that bends it upwards, at the top, the moment that skin goes into compression is going to buckle. But since the spars can still transfer that load, you don't have that issue with the buckling becoming unstable. It's simply a case of the skin doesn't help transfer that load. The skin is there to transfer the normal pressure to the spars, and then from there to the rest of the model. Okay, so that's just a special kind of an element that helps you to model that. So one of the assumptions for that element is it doesn't have bending stiffness, and again, only the in-plane shear effects that you have. Okay, so that's just a slight additional one that I want to mention because I recently had to help somebody with this model again.
All right, thank you very much for everyone joining. We will make a recording of this session available and publish the link as soon as possible to everybody's email addresses that were registered for this session. Thank you very much.